Chapter 5, Section 4, Factoring Special Trinomials, specifically perfect square trinomials. So it says, factor each trinomial and indicate which ones are perfect squares. Okay, well, how can a trinomial be a perfect square? Well, I have x squared plus 10x plus 25. There's no coefficient in front of here, so that means if this is factorable, it's got to be one of the easier ones. We need two numbers that multiply to 25 but add to 10. Well, that's easy enough to identify. It's 5 and 5. So I can factor this very quickly. Okay, but you've seen trinomials like this before. Sometimes when you factor them, the two binomials that you get are the same. That doesn't always happen. In fact, it usually doesn't happen. But when it does, it allows us to write the factored form like this. Okay, hence I can write it as a perfect square. So this is what we call a perfect square trinomial because it is factorable and both binomials are the same. Let's try another one. Here I need two numbers that multiply to 36 but add to negative 12. Well, I think negative 6 and negative 6 will do the trick. Just watching your signs. And lo and behold, they're the same. Therefore, this can be written as a perfect square. So this is a perfect square trinomial. How about this one? Two numbers that multiply to 36 and add to 13. I believe the numbers we're looking for are 9 and 4. Those add to 13, multiply to 36, but these binomials are not the same. Okay, so this is factorable, but it is not a perfect square trinomial. Okay, really that's all there is to it. It's pretty simple. Factor these quickly. What numbers multiply to 1 but add to negative 2? Negative 1, negative 1. They are the same. So it can be written as a perfect square. So, yes. Next one. Ooh. Well, let's look for a GCF. There isn't one. So unfortunately in this case we are stuck with the 2. So this is the more complicated variety. Okay. So we want two numbers, not that multiply to 6, but multiply to 12. But at the same time, add to 7. Okay. So I'm going to demonstrate the shortcut method. So we go straight to the factored form right away. This is a 2x squared, so I write 2x twice. All right. Now we have to find the two numbers at work. What multiplies to 12 and adds to 7? That would be 3 and 4. Or 4 and 3. Of course, to finish it, we have to divide out anything that's in common. I can tell already this is factorable, but it's not a perfect square. But I'll just finish it anyway. I get x plus 2 and 2x plus 3. Okay. So that's the factored form, but these binomials are not the same. Okay. You can also kind of tell by looking at it. Since this 2 is not factored out, the only way this could be a perfect square trinomial is if this coefficient here was a perfect square. And it's not. All right. One more. Look for a GCF, and there isn't one. Okay, so we need two numbers that multiply to 36 but add to 12. Okay, so this is 4x squared, so I write 4x twice, no square. And numbers that multiply to 36 and add to 12, well, that would be 6 and 6. Okay. I can already tell this is a perfect square trinomial because these are the same, even though I'm not done yet. Okay, I have to divide out everything that is in common. So this is going to give me 2x plus 3 times 2x plus 3. Completely factored, but of course it's the same. So I can write this as 2x plus 3 in brackets, all squared. And there we go. So the answer is Yes. 4 of them were perfect square trinomials, 2 of them were not. All right, so let's get our definition formally. A factorable trinomial with 2 equal binomial factors is called a, newsflash, perfect square trinomial. That's it. Below it says, factor the following perfect square trinomials. Do you see a pattern? So in fact, we're already told that all of these are going to be perfect squares, but we want to look for a pattern. Maybe that'll help us identify a perfect square trinomial just by looking at it without having to factor. Let's see what happens. All right, so we need numbers that multiply to 9 but add to 6. Well, notice how 9 is a perfect square. And the number we're looking for, the numbers are 3 and 3. Notice how 3 is half of 6. Speculation, but maybe that has something to do with it. So the key number was 3. Okay? It is the square root of the last number, 9, and it happens to be half of the middle number, 6. Well, let's see if that works. All right, next one. What multiplies to 16 adds to 8? Well, 16 is a perfect square. The square root of that is 4. And what do you know? 4 happens to be half of this middle coefficient. You don't have to think about it this way. You can just factor it as you normally would, and then you'd get 2 identical binomials. But I think we're starting to see a pattern, is that the number here is the square root of the last and half the middle, providing that the leading coefficient here in front of the x squared is a 1, which we typically never write. Next one, we want to multiply to 81 but add to negative 18. Okay. Well, the square root, or should I say the principal root of 81 is 9. But remember, 9 is not the only number that I can square to get 81. There's another number as well. That would be negative 9. And that's the one we need, because half of negative 18 is negative 9. And there we go. Okay. Double check. Square negative 9, positive 81. And if you double negative 9, you get negative 18. So I think it's pretty safe to say we've identified the pattern. Without factoring completely, determine which trinomials are perfect square trinomials. So let's try to use this pattern that we identified above and put it to the test. All right, so this is an invisible 1, so we want 2 numbers that multiply to 25 and add to 26. Hopefully that are the same. Okay, well 25 is a perfect square, so the numbers that we would need are 5 and 5. But unfortunately they do not add to 26. So I can tell you already, no, it is not a perfect square trinomial. It is factorable though. Okay. 2 numbers that make it factorable are 25 and 1. But of course these binomials are not the same, so it's not a perfect square trinomial. Okay. Next. Okay. Well, here's the dead giveaway. Even though 36 is a perfect square, we need to think of this as a negative 36. Okay. Well, you can't take the square root of a negative number and get a real answer. It can't be done. Right? When you take any number that's positive and you square it, it's positive. Even if you take a negative number and you square it, you still get something positive. So I can tell already this is no. Okay? Because you cannot take the square root of negative 36 and get a real number. Does that mean this isn't factorable? I know it says we don't have to, but at least we've identified that it's not a perfect square. Numbers that multiply to negative 36 add to 5. I believe that is positive 9, negative 4. Yeah. Next one. Okay. We've got a negative 2 in front. Okay, so let's see if we can identify a GCF. And yeah, I believe it is a 2. And it is negative. So even though the GCF is a 2, it would be beneficial if I can factor out this negative. So I'm going to do that. Just remember it's going to change all your signs. So I have positive x squared. This is going to become positive 22x. And this is going to become positive 121. Okay? I mean, technically speaking, it's already not a perfect square trinomial, but if I only concentrate on this trinomial here, it is. Okay, we have positive 121. That's a perfect square, and the square root of that is 11. And 11 is half of 22. So I'll factor it. Why not? Why not? I already know it is, so there's no harm in showing it. Okay. So this part here is a perfect square trinomial. So I guess we can say yes.